A captivating hook. Imagine the universe as a vast, silent ocean, and then picture a ripple, not of water, but of reality itself. This ripple, subtle and imperceptible to the casual observer, moves through the very fabric of existence, carrying with it echoes of events both ancient and unseen. It is a whisper of creation, a vibration of the cosmos that threads through time and space, shaping galaxies, stars, and the invisible scaffolding that holds the universe together. In this imagined expanse, one senses a rhythm, a pulse that hums beneath the apparent stillness, hinting at profound secrets that our minds are only beginning to grasp. The ocean stretches endlessly, its surface calm yet deceptive. Beneath it lies a hidden turbulence, currents that twist and churn in patterns too complex for our senses to follow. Each ripple, each disturbance, is a story, a transformation, a rearrangement of reality at its most fundamental level. To observe it is to confront the profound intricacy of existence, where even the smallest perturbation resonates across unimaginable distances. The ripple is silent, yet it carries knowledge older than stars, memories encoded in the very structure of spacetime, waiting for those who dare to perceive them. As the ripple moves, it interacts with everything it touches, bending and shifting, transforming the landscape of reality subtly but irrevocably. A single vibration may set off a chain of events that echoes through cosmic time, influencing the birth of a star or the collapse of a distant galaxy. The universe, though appearing tranquil and eternal, is alive with these hidden dynamics, a theater of unseen forces playing out in patterns beyond comprehension. Each ripple is both a messenger and a sculptor, shaping the cosmos in ways that hint at intelligence or design, yet defy ordinary understanding. Consider the ripple as it passes through what we perceive as emptiness. To the eye, nothing seems to exist, a void stretching infinitely, but this emptiness is full of potential, of energy and latent possibilities. The ripple awakens this potential, stirring fields of invisible matter and energy into motion. It is as if reality itself listens, responding to the imperceptible coaxing of the ripple, bending subtly in obedience to laws we only half understand. What we call vacuum is not void but a rich canvas, vibrating with hidden patterns that ripple across the cosmos like the quiet heartbeat of the universe. Time, in this vision, is not a straight line but a pliable, flowing dimension that bends and stretches with each ripple. The past and the future, though seemingly separate, are connected by these undulations, which carry information across epochs. A ripple that begins in a moment now might carry fragments of the first light of creation, or a whisper of events yet to come. To sense such a ripple is to sense the unity of all things, the interconnectedness of moments that our conscious minds usually perceive as isolated. It is a hum of eternity, a reminder that the universe remembers, and perhaps even anticipates. Light, too, dances to this hidden rhythm. Photons travel in ways guided not just by simple geometry, but by the undulating contours of reality itself. The ripple bends and refracts, shaping the course of beams that traverse unimaginable distances. Galaxies shimmer and glow not merely as isolated islands, but as participants in an intricate ballet choreographed by these subtle oscillations. Even the most distant quasar, piercing through cosmic darkness, is touched by the ripple, its light carrying whispers from a reality that defies ordinary intuition. Each beam is a storyteller, narrating the universe's secret language. Gravity, often considered a constant, is revealed in this vision to be more flexible, more responsive than we imagine. The ripple, though imperceptible in magnitude, can influence the paths of stars and planets, nudging them with a delicacy that seems almost conspiratorial. This is a universe alive with subtle interactions, where cause and effect are woven together by threads too fine for mere observation. One begins to sense the universe as a vast, resonant network, where the tiniest perturbations can cascade into monumental transformations, leaving imprints on the cosmic web that span billions of light-years. As the ripple reaches denser regions of matter, its effects become more pronounced, bending atoms and molecules in gentle, deliberate motions. Chemical reactions, the folding of proteins, even the slow rotation of planets can all be influenced, minutely but decisively, by the passage of these subtle oscillations. It is a reminder that no part of existence, no matter how seemingly solid or immutable, is isolated. The universe participates in a silent dialogue, a perpetual exchange of energy and information mediated by waves that we are only beginning to sense, yet which have shaped everything we know. Sound, though absent in the vacuum of space, has its counterpart in the ripple's effect on energy and fields. One can imagine a symphony of invisible frequencies, each vibration resonating in the hearts of stars, within the cores of planets, and through the voids between. These vibrations encode histories, secrets of creation, and the intricate choreography of matter and energy. To attune oneself to this symphony is to perceive existence from a new vantage, where life and death, creation and destruction, are all notes in a universal melody. The universe hums with a depth of meaning that transcends ordinary perception. Time dilates and contracts in response to these ripples, subtly altering the perceived rate of events. An observer might notice seconds stretching into minutes, or epochs condensing into moments, without apparent cause. This is not magic but the natural consequence of a reality in constant vibration, where spacetime is malleable and sensitive to the subtlest influences. The ripple is a messenger of change, a herald of the universe's responsiveness, reminding us that what seems absolute is often pliable, and that our perception is limited by the narrow lens through which we view the cosmos. Even the most fundamental particles are not immune. Electrons, quarks, neutrinos, they all dance in patterns dictated by the undercurrents of reality. Their motions, though imperceptible, cascade into larger structures, giving rise to chemistry, biology, and the phenomena we call consciousness. Each ripple is a sculptor, carving out the framework of existence at every scale, from the infinitesimal to the cosmic. The very laws of physics, seemingly rigid and eternal, may themselves be participants in this subtle ballet, bending ever so slightly in response to the undulating tides of reality. As the ripple propagates, it interacts with other ripples, colliding and intertwining in complex patterns. These interactions can amplify certain effects while cancelling others, creating a dynamic, ever-shifting tapestry. It is a dance of probabilities, a network of possibilities that constantly reconfigures itself. The universe is alive with potential, and every ripple adds a brushstroke to the vast painting of existence. To witness this interplay is to glimpse the mind of the cosmos, to understand that creation is not static but a continuous, flowing conversation across time and space. Space itself, often thought of as empty, is revealed as a pliable medium, sensitive to the minutest disturbances. The ripple compresses and stretches regions, subtly influencing the geometry of galaxies, the shape of orbits, and the distribution of cosmic matter. Dark matter and dark energy, mysterious and elusive, may be conduits through which these ripples propagate most effectively, hinting at hidden layers of reality that interact silently with the observable universe. Each wave is a key, unlocking dimensions of understanding that have remained just beyond the reach of observation. As the ripple moves outward, it carries with it echoes of causality, stretching the idea of cause and effect across vast distances. One event here may influence another billions of light-years away, not through direct interaction but through the gentle undulations of reality itself. The universe becomes a network of interconnected moments, each ripple a thread linking seemingly disparate phenomena. In this vision, isolation is an illusion, and every action resonates far beyond its apparent sphere, shaping the tapestry of existence in ways subtle, profound, and enduring. Consider the possibility that consciousness itself is attuned to these ripples, sensitive to vibrations that the senses cannot perceive. Thoughts, emotions, and intuitions may be faint reflections of cosmic undulations, impressions of the universe communicating with itself through its most complex creations. Each mind becomes a resonant chamber, vibrating in harmony or dissonance with the hidden tides of existence. The ripple is no longer merely physical, it is a bridge connecting awareness to the subtle mechanisms of reality, hinting that understanding and perception may themselves be woven from the same fabric. In imagining the ripple, one also confronts the paradox of permanence and change. Structures seem solid and unyielding, yet they are perpetually influenced by unseen waves. Mountains erode, stars collapse, civilizations rise and fall, all subtly guided by these imperceptible motions. The ripple is a reminder that stability is relative, and that change is a fundamental property of reality. To observe this is to cultivate humility, to recognize that even the most enduring phenomena are, at their core, subject to the quiet, unceasing rhythm of the cosmos. The ripple does not discriminate. It passes through order and chaos alike, weaving patterns in both the structured and the random. Galaxies spiral gracefully, black holes consume matter with fierce precision, and yet each is touched by the same subtle undulations. Even the apparent randomness of quantum events may be part of the ripple's grand design, a dance of probabilities orchestrated by forces that transcend conventional understanding. In this light, the universe appears not as a collection of isolated phenomena but as a unified, vibrating whole, alive with subtle interactions at every scale. Patterns emerge when one studies the ripple closely, hints of symmetry and elegance in the fabric of reality. Fractals unfold, spirals recur, and echoes of structures repeat across scales. These patterns are not merely aesthetic but functional, governing the stability of matter, the formation of galaxies, and the emergence of complexity. The ripple is both the cause and the reflection of these recurring motifs, a signal of the inherent intelligence or order embedded in the cosmos. One begins to perceive a universe that is self-aware, or at least self-organizing, where subtle vibrations encode profound coherence. Time itself seems to hold its breath as the ripple passes. Moments that felt transient become meaningful, and events that seemed isolated reveal their connections. The universe is a vast network of influence, and the ripple traces the threads linking past, present, and future. To follow it is to move through the cosmic narrative, witnessing the interplay of forces that shape everything from the smallest particle to the grandest galaxy. Each ripple is a stanza in an eternal poem, a verse of creation written across the boundless canvas of space-time. Even the observer is transformed by the ripple, subtly influenced by the awareness of these hidden motions. Perception becomes more sensitive, intuition sharper, imagination more attuned to the underlying rhythm of reality. The universe ceases to be a passive backdrop and becomes an active participant in experience, responding to curiosity, attention, and understanding. The ripple bridges the gap between observer and observed, hinting that consciousness and cosmos are intertwined in ways profound, subtle, and inescapably intimate. Finally, the ripple is a meditation on existence itself. It reminds us that the universe is alive with motion, even when all seems still, that reality is richer and more intricate than perception suggests, that every moment is part of an endless interplay of forces and possibilities. By imagining this ripple, we step into a deeper understanding, a contemplative space where knowledge, wonder, and humility coexist. In the quiet resonance of the cosmic ocean, we hear the whisper of creation, the rhythm of reality, and the enduring mystery of what it means to exist. Briefly introduce gravitational waves as predicted by Einstein and the groundbreaking discovery. Albert Einstein, in his theory of general relativity formulated in 1915, suggested that massive objects warp the fabric of space-time, and that accelerating masses could generate ripples traveling through this very fabric. These ripples, called gravitational waves, would propagate at the speed of light, carrying with them information about the violent cosmic events that created them. For decades, this remained a theoretical prediction, a whisper of mathematics rather than a phenomenon one could observe directly, an invisible vibration stretching and compressing the universe itself. Einstein himself was skeptical about the detectability of gravitational waves. The distortions they caused were predicted to be extraordinarily small, vanishingly so, even from cataclysmic events such as colliding black holes or exploding stars. The idea that one could measure such infinitesimal shifts in spacetime, fractions of the width of a proton across kilometers of distance, seemed almost fantastical. Yet, this was not a limitation of physics, but of human ingenuity and technological reach. For nearly a century, scientists wrestled with the challenge of designing instruments sensitive enough to detect these elusive cosmic whispers. The theoretical importance of gravitational waves cannot be overstated. Unlike light, which can be blocked, absorbed, or scattered, gravitational waves pass through all matter virtually unimpeded. They carry direct, unaltered information from their sources, offering a window into phenomena invisible to traditional telescopes. Events that emit little or no electromagnetic radiation, such as the merger of black holes, become accessible through these ripples. This prospect expanded our understanding of the cosmos, promising a new method of observation and revealing aspects of the universe that had remained completely hidden until now. Decades of research culminated in the creation of extraordinarily sensitive detectors. Chief among them is LIGO, the Laser Interferometer Gravitational Wave Observatory, with facilities in Louisiana and Washington in the United States. These instruments use laser beams bounced along long, perpendicular arms to measure the tiniest distortions in spacetime. The principle is deceptively simple. As a gravitational wave passes, it slightly stretches one arm while compressing the other, altering the interference pattern of the lasers. The engineering required to achieve the necessary precision, however, is immense, pushing the limits of optics, vacuum technology, and vibration isolation. The first direct detection of gravitational waves occurred on September 14, 2015, a historic event that sent ripples of excitement through the scientific community. The waves originated from a pair of black holes spiraling into one another over 1 billion light-years away. As they merged, they released energy equivalent to several solar masses in mere seconds, radiated not as light, but as distortions in spacetime itself. LIGO recorded the characteristic chirp, a signal increasing in frequency and amplitude as the black holes approached collision, a precise match to predictions from Einstein's equations. This discovery was groundbreaking on multiple fronts. It confirmed a central prediction of general relativity that had remained unverified for a century, providing direct evidence that spacetime itself can oscillate. It also inaugurated an entirely new branch of astronomy, gravitational wave astronomy. For the first time, humanity could hear the universe in addition to seeing it. This dual sensory approach promises insights into the most extreme events in the cosmos, allowing scientists to probe black hole dynamics, neutron star mergers, and potentially even echoes from the early universe itself. Neutron star collisions, in particular, became accessible through gravitational wave detection. Unlike black holes, neutron stars can emit electromagnetic radiation, allowing simultaneous observation with both gravitational and traditional telescopes. Such multi-messenger astronomy provides unprecedented opportunities for understanding fundamental physics, such as the origin of heavy elements like gold and platinum. The 2017 detection of a neutron star merger confirmed this, with both gravitational waves and gamma-ray bursts observed, giving scientists a complete, cross-validated picture of the cosmic cataclysm. Beyond astronomy, gravitational waves offer a unique laboratory for testing the nature of gravity itself. By comparing observations with Einstein's predictions, scientists can search for deviations that might hint at new physics. So far, all observations have been consistent with general relativity, but continued detections push the boundaries, probing regimes of extreme gravity, unreachable by any other means. These measurements can help refine our understanding of spacetime, the behavior of matter under extreme conditions, and even the possible existence of exotic objects like primordial black holes or cosmic strings. The sensitivity required to detect these waves is almost inconceivable. LIGO can measure distortions smaller than 1,000th the diameter of a proton over 4 kilometers. To achieve this, every possible source of noise, from seismic vibrations, thermal fluctuations, to even passing trucks, must be accounted for and minimized. Advanced technologies such as suspended mirrors, vacuum tubes spanning kilometers, and precise laser stabilization all combine to create the delicate balance required for measurement. This represents a triumph of both physics and engineering, showcasing humanity's ability to perceive the imperceptible. Collaborations across the globe, including Virgo in Italy and Kagra in Japan, have joined in this effort, increasing detection sensitivity and allowing precise triangulation of wave sources. With multiple observatories, scientists can determine the location of cosmic events with remarkable accuracy, enabling follow-up observations with telescopes. The international cooperation also fosters shared knowledge, standardized protocols, and a richer understanding of gravitational wave phenomena, demonstrating how a global scientific effort can reveal the deepest secrets of the cosmos. Each detection also provides a glimpse into the life cycles of black holes. The first LIGO event, and subsequent observations, revealed black holes far larger than previously expected, challenging models of stellar evolution. These cosmic giants, born from massive stars, merge in ways that emit tremendous energy in gravitational waves. By analyzing the frequency and amplitude of these signals, scientists can infer the masses, spins, and orbital dynamics of the colliding objects, creating a new census of black holes and deepening our understanding of the formation and evolution of these enigmatic entities. Gravitational waves also carry information about the structure of spacetime itself. As they propagate, they might reveal subtle effects of cosmic expansion or interactions with dark matter. Future generations of detectors, including space-based observatories like LISA, aim to capture lower frequency waves, opening the possibility of studying supermassive black hole mergers and even primordial signals from the early universe. These advancements could provide insight into conditions immediately following the Big Bang, potentially offering clues about inflation, the first moments of cosmic history, and the fundamental nature of gravity. The implications for fundamental physics are staggering. Observing gravitational waves allows for direct tests of the speed at which they travel, confirming that they move at the speed of light within extremely tight margins. This constraint rules out certain alternative theories of gravity and informs models of dark energy and cosmic acceleration. By measuring the polarization of waves, scientists can explore whether spacetime behaves precisely as general relativity predicts or if subtle deviations hint at new interactions. Each ripple detected is not merely an astronomical event but a laboratory for the laws governing reality itself. Gravitational waves also reveal the frequency of cosmic mergers. By building catalogs of events, astronomers can estimate how often black holes collide, how neutron-star mergers contribute to chemical enrichment, and how galaxies evolve through these violent interactions. This statistical approach transforms our understanding of the universe from static observation to dynamic modeling, tracing the life cycle of matter and energy over billions of years. The waves are not just ephemeral blips, they encode the narrative of cosmic evolution, allowing us to reconstruct events invisible to conventional observation. Public fascination with gravitational waves has grown rapidly, as these discoveries connect human imagination with the deepest mysteries of the universe. The detection of these signals transforms abstract mathematical predictions into tangible phenomena, accessible to human understanding. Headlines describe black holes colliding billions of light-years away, releasing energy beyond comprehension, yet the instruments on Earth capture their delicate whisper. This juxtaposition of immense cosmic violence with exquisite measurement captures the imagination, inspiring new generations of scientists and expanding humanity's sense of place in the cosmos. Gravitational waves also challenge our perception of the universe's quietude. Space, once considered a tranquil vacuum punctuated by stars, is instead revealed as a dynamic medium, alive with waves from countless events. Each ripple, imperceptible to ordinary senses, testifies to the ceaseless activity of matter and energy. Even distant, silent regions of space are part of this ongoing vibration, reminding us that the universe is not static but a constantly resonating entity. In this way, the discovery of gravitational waves reshapes not only science but also our philosophical and aesthetic understanding of existence. The technology behind detection continues to evolve. LIGO and Virgo are being upgraded, and new facilities promise even greater sensitivity. Quantum-enhanced measurement techniques, cryogenic mirrors, and longer baseline detectors aim to detect weaker and more distant waves, pushing the frontier of observable phenomena. Each improvement expands the window through which humanity perceives the cosmos, allowing detection of events previously unimaginable, from quiet neutron star in spirals to potential echoes of phenomena from the earliest moments of the universe. Gravitational wave astronomy also serves as a tool for testing extreme states of matter. Neutron stars, for instance, are composed of matter compressed to densities unimaginable on Earth. Observing their mergers through gravitational waves reveals how such matter behaves under intense gravity, providing insight into nuclear physics in regimes impossible to recreate artificially. These observations deepen our understanding of fundamental forces and may hint at new physics, bridging astrophysics, particle physics, and general relativity in ways that were once purely theoretical. The discovery has accelerated theoretical modeling, as astrophysicists attempt to match observations with detailed simulations. Supercomputer models simulate billions of particles interacting under extreme gravity to predict waveforms. Comparing these predictions with observed signals allows scientists to refine models of stellar evolution, black hole formation, and cosmic dynamics. Each detection serves as a feedback mechanism, validating theories, adjusting parameters, and continuously improving our understanding of the universe's most dramatic events. As detections accumulate, patterns emerge. Certain types of mergers are more common than others, revealing the distribution of black hole masses and spins. Some signals hint at hierarchical mergers, where black holes formed from previous collisions merge again. These observations provide insights into galactic evolution, stellar population dynamics, and even the role of dense star clusters in producing massive black holes. Gravitational waves are not random. They encode structure, history, and process, offering a map of the universe's violent and creative activities. The journey from Einstein's theoretical prediction to the first detection is a testament to human perseverance. Generations of physicists, engineers, and mathematicians contributed, often over decades, to turn an almost impossibly delicate measurement into a reality. The successful observation demonstrates the power of collaboration, patience, and ingenuity, showing that even the most subtle predictions of nature can be confirmed with enough dedication. It is a triumph not just for science, but for the spirit of inquiry itself, proving that curiosity can indeed overcome seemingly insurmountable challenges. In conclusion, gravitational waves transform our understanding of the cosmos. From abstract ripples predicted a century ago to tangible signals recorded on Earth, they provide a novel lens to study the universe's most violent and mysterious events. They reveal the hidden dynamism of spacetime, offer a direct probe of extreme gravity, and open a new chapter of multi-messenger astronomy. With each detection, we expand the boundaries of knowledge, bridging theory, observation, and imagination, and tuning into the universe's own hidden music, a song that has resonated across billions of years and countless light-years of space. tease the fundamental question: are we truly seeing space-time bend and stretch right before our eyes? At first, the question feels almost absurd. How can the invisible fabric of reality, which seems so immutable and intangible, be directly observed? And yet, with the detection of gravitational waves, we are confronted with exactly that possibility. Minute distortions in spacetime caused by cataclysmic cosmic events, traveling billions of light-years to reach us. Each signal recorded is a subtle but concrete signature of geometry itself in motion, a direct encounter with the dynamic essence of the universe. The idea that space and time are malleable is counterintuitive. To our daily experience, distances and durations appear fixed, clocks tick steadily, and rulers measure consistent lengths. But in Einstein's vision, the very coordinates of space and time are not fixed but dynamic, responsive to mass and energy. Gravitational waves offer a rare glimpse of this principle in action, as vast regions of the universe oscillate imperceptibly, stretching and compressing the distances between objects. These shifts, though tiny, confirm that spacetime is not merely a passive stage but an active participant in the cosmic drama. Observing this bending requires instruments of extraordinary precision. LIGO and similar observatories are designed to measure changes in distance smaller than a proton across kilometers. When a gravitational wave passes, one arm of the interferometer stretches ever so slightly while the perpendicular arm contracts, producing a measurable interference pattern in laser light. The effect is astonishingly small, yet unequivocal. In essence, we are witnessing a minuscule, precise deformation of spacetime itself, a whisper from the universe that tells us, quite literally, that space and time are alive and responsive. The question also invites deeper philosophical reflection. If spacetime can bend and stretch in response to distant events, what does that mean for our perception of reality? Every gravitational wave implies that the universe is not a static arena but a fluid, interconnected medium. Events occurring billions of light-years away ripple across this medium, subtly influencing regions that seem isolated. It challenges the notion of separateness, suggesting that cosmic phenomena are linked in ways our senses rarely apprehend, and that even the emptiest stretches of space are engaged in a perpetual, dynamic conversation. The bending of spacetime is not just a curiosity, it is a messenger. Each wave encodes details about the mass, spin, and orbit of colliding black holes or neutron stars. By analyzing the waveform, scientists can reconstruct the violent dynamics of these events with remarkable accuracy. The signal contains the story of spacetime itself stretching and compressing under extreme gravitational forces, revealing the hidden choreography of cosmic collisions. In this sense, gravitational waves are not just observations, they are narratives written directly into the structure of reality. Even the notion of seeing spacetime bend stretches the imagination. We are not observing with eyes, but with instruments that translate infinitesimal distortions into comprehensible signals. The chirps and hums captured by LIGO are our sensory translation of geometry in motion. Each detection allows us to convert abstract mathematics into something almost tangible, a rhythm of stretching and compression, a pulse of reality that bridges the gap between theory and observation. Through this lens, the universe itself becomes perceptible in a profoundly new way. Yet, skepticism is natural. The changes in spacetime are so minuscule that they might seem like theoretical constructs rather than observable phenomena. But repeated detections and cross-verifications between multiple observatories leave little room for doubt. Independent signals captured at different locations corroborate the same event, confirming that the observed distortions are real and propagate across the cosmos. These measurements are not hypothetical. They are consistent, reproducible evidence that spacetime bends and stretches in accordance with Einstein's predictions. The bending and stretching is also a dynamic process, revealing that spacetime is not static. During a merger of massive black holes, for instance, Spacetime is violently contorted, sending ripples outward in all directions. As the wave propagates, it oscillates, compressing and stretching regions along perpendicular axes. To imagine this is to visualize the universe as a vast, vibrating membrane, responsive to the dance of mass and energy. Each ripple is a testament to the elasticity of reality, a phenomenon both awe-inspiring and humbling in its scale and subtlety. Time itself is implicated in this bending. Gravitational waves are fluctuations not just in space but in spacetime, meaning that the intervals between events can stretch and shrink. For a passing wave, clocks along one axis tick fractionally faster or slower relative to others. The universe is revealed to be a medium in which time and space are not rigid, but intertwined and flexible, responding to cosmic forces. Observing this effect directly, even indirectly through instruments, challenges our intuitive understanding and invites a deeper appreciation of the universe's profound complexity. The detection of these waves also alters our sense of distance and simultaneity. Events billions of light-years away can influence our instruments here, and yet the waves carry precise information about when and where the originating event occurred. The bending and stretching of spacetime is therefore both local and global, demonstrating that the universe is a connected system in which geometry itself participates in communication. What we witness is a subtle cosmic echo, a deformation that carries the imprint of faraway energies through the continuum of spacetime. Even regions that appear empty are not exempt from bending. Gravitational waves travel unimpeded through matter, traversing galaxies, nebulae, and voids alike. This means that the structure of spacetime is universally malleable, responding to forces across the vastness of the cosmos. The emptiness of space is filled with latent potential, a medium capable of vibration and response. Every wave passing through is a testament to the fluidity of reality, confirming that nothing is entirely isolated and that the universe's architecture is alive with subtle motion. The question also carries emotional weight. Witnessing spacetime bend is witnessing the universe in motion on the most fundamental level. It is a direct connection to events of unimaginable scale: black holes colliding, stars collapsing, neutron stars merging. In a single waveform, we perceive epochs of cosmic violence, billions of years of history, and the universality of physical law. This perspective is both humbling and exhilarating, reminding us of our place in a vast, dynamic cosmos that communicates through ripples in the very structure of reality. To perceive spacetime bending also demands imagination and abstraction. One must stretch beyond ordinary sensory experience to comprehend distortions measured in fractions of a proton width. The human mind, unaccustomed to such scales, relies on visualization, analogy, and mathematical modeling. Yet, these efforts are not mere intellectual exercises, they are genuine ways to connect with the universe's subtle motions. Through careful observation, simulation, and thought, we translate imperceptible vibrations into comprehensible phenomena, turning theoretical geometry into tangible understanding. Gravitational waves further reveal the interplay of extremes. The most powerful signals come from collisions of black holes many times the mass of the Sun. The bending and stretching of spacetime near these events is immense, yet by the time the waves reach Earth, the distortions are microscopic. This juxtaposition between the colossal and the infinitesimal underscores the delicate balance of the cosmos: immense energy propagated as tiny shifts in geometry, detectable only through the most precise instruments. Observing this is witnessing the universe's paradoxical elegance. The bending is also a reminder of the limitations of perception. To see spacetime distort directly would require senses attuned to dimensions beyond human capability. Instruments act as extensions of perception, amplifying and translating what is otherwise invisible. In this sense, gravitational wave astronomy expands human consciousness, enabling us to perceive phenomena that are simultaneously real and imperceptible. The universe, through these waves, invites us to rethink the boundaries of observation, demonstrating that what is unseen can still exert profound influence. Even subtle bends and stretches of spacetime encode enormous energy. A black hole merger releases gravitational radiation equivalent to several solar masses within seconds, illustrating that the curvature of spacetime carries both information and power. These distortions are not merely passive, they are active expressions of cosmic energy, traveling across the void to imprint their signature on distant observers. In observing them, we witness the energy of spacetime itself in motion, a dynamic theater in which geometry and force are inseparable. Each detection offers lessons about the geometry of the universe. Waveforms reveal the orientation, spin, and mass of colliding bodies, effectively mapping spacetime distortions. The stretching and compressing of distances encodes these details, enabling scientists to reconstruct the events with precision. Spacetime is not only bending, it is carrying a detailed narrative, a record of cosmic interactions encoded in its geometry. Observing this is akin to reading the autobiography of the universe written in the language of curves and ripples. The act of measuring these waves is an interaction with reality itself. Every time LIGO or Virgo records a signal, human ingenuity touches spacetime, interpreting its motions and confirming Einstein's century-old predictions. It is a meeting of thought and matter, theory and observation, mind and cosmos. The bending and stretching are real, and yet they also exist in the interface between human understanding and natural law. Each observation is simultaneously empirical proof and philosophical reflection. Cosmic distances are also contextualized through bending. The amplitude of a gravitational wave diminishes with distance, allowing scientists to estimate the location of events across billions of light-years. By measuring the wave's effects on spacetime here on Earth, we connect to occurrences so distant that they belong to an entirely different epoch. This connection between near and far, present and ancient, reveals the universe as an integrated continuum, where bending and stretching of geometry acts as a bridge linking all points across space and time. The bending phenomenon also reinforces general relativity's core idea: mass and energy dictate the curvature of spacetime. Gravitational waves are the dynamic manifestation of this principle, showing that spacetime is flexible, responsive, and capable of propagating information. Observing these distortions validates the profound insight that reality is not a static stage but a living, reactive fabric. Each measurement is confirmation that Einstein's vision, formulated with pen and paper, accurately describes phenomena billions of light-years away. Even mundane concepts of distance, time, and simultaneity are challenged. The stretching of spacetime implies that the distance between 2 points is not absolute but can oscillate in response to distant events. Similarly, intervals of time can subtly differ depending on orientation relative to a passing wave. Our ordinary intuitions fail at these extremes, but instruments allow us to quantify the oscillations, revealing a universe more fluid and interconnected than everyday experience suggests. Bending and stretching are thus both physical reality and conceptual revelation. The question also invites wonder about what we cannot yet see. Gravitational waves detected so far are the strongest signals from the most extreme events, but countless weaker ripples pass unnoticed, traveling through galaxies and voids. The universe is alive with these subtle distortions, a vast ocean of geometric vibration. Detecting them all is beyond current technology, yet imagining their existence expands our appreciation of cosmic complexity, reinforcing the idea that bending and stretching of spacetime is a pervasive, universal phenomenon. Finally, the bending and stretching is a meditation on impermanence and motion. Even the fixed structure of spacetime is dynamic, oscillating, and responsive. Gravitational waves remind us that the universe is not frozen, it is a continuous flow, a dance of energy and geometry in which nothing is entirely stable. Observing these ripples, we confront the fundamental fluidity of reality itself, perceiving the universe as a living fabric whose every movement, however slight, carries stories of immense cosmic events, energy, and time. Simplify the concept of spacetime. Think of spacetime not as empty space, but as a flexible fabric that pervades everything. This fabric is not made of threads or fibers, but of the very geometry of reality, entwining the three dimensions of space with the passage of time. Every mass, from the smallest particle to the largest galaxy, sits upon this fabric and bends it according to its weight and motion. The bending is not merely metaphorical, it is a measurable deformation that affects the motion of nearby objects, guiding planets in their orbits and dictating the trajectory of light across the cosmos. Imagine placing a heavy ball on a stretched rubber sheet. The sheet dips and curves under the weight, influencing the path of smaller balls rolling nearby. This analogy helps visualize how spacetime responds to mass. It bends, stretches, and warps in response to energy. A planet like Earth orbits the Sun not because of an invisible force pulling it in the traditional sense, but because it follows the curvature of spacetime created by the Sun's mass. In this way, gravity is geometry in action, a natural consequence of spacetime's flexibility rather than an external force acting at a distance. The fabric of spacetime is continuous, unbroken, and all-encompassing. It is not a backdrop against which events unfold, but an active participant in the cosmic story. Every motion, collision, or explosion interacts with this fabric, creating ripples and waves that propagate outward. These ripples are gravitational waves, subtle deformations traveling through the continuum, carrying information about their sources across unimaginable distances. The universe is therefore a dynamic interplay of matter, energy, and geometry, each influencing the others in a delicate, ongoing dance. Light itself travels along this fabric, its path curved by the deformations of space-time. A beam from a distant star bends as it passes near a massive object, an effect known as gravitational lensing. This phenomenon allows astronomers to observe objects otherwise hidden behind cosmic obstacles and provides a striking confirmation that spacetime is indeed flexible. It responds to mass and energy, guiding both matter and radiation along the contours of its geometry, illustrating the profound interplay between the shape of reality and the objects within it. Even time is affected by the curvature of spacetime. Near a massive object, time runs more slowly relative to a distant observer, an effect confirmed by precision clocks on Earth and in orbit. This temporal stretching and compression is part of the fabric's behavior, inseparable from spatial curvature. Time and space are interwoven. One cannot bend without influencing the other. The elasticity of spacetime is therefore multidimensional, shaping both where objects are and when events occur, offering a unified framework to understand the cosmos. Spacetime is not uniform. Regions with more mass create deeper curves, while empty stretches remain relatively flat. This unevenness produces the gravitational landscapes that govern cosmic motion. Galaxies form along the valleys and ridges of this landscape, while stars, planets, and moons trace paths determined by these geometric contours. Even subtle perturbations, such as passing gravitational waves, propagate through these regions, inducing minute stretching and compressing that, while imperceptible to ordinary senses, can be measured with advanced instruments. The flexibility of spacetime implies that no object exists in isolation. The presence of one mass subtly affects the curvature experienced by another, linking distant regions in a complex network of geometric interactions. Every gravitational interaction, from a falling apple to a colliding galaxy, is mediated by the bending of this fabric. Spacetime is not a passive arena but a responsive medium, registering every influence, every motion, and every collision, creating a rich tapestry of interactions that underlies all of cosmic dynamics. The analogy of a fabric also helps in understanding gravitational waves. When massive bodies accelerate, They create ripples in the spacetime fabric, similar to disturbances moving across a stretched sheet. These waves travel at the speed of light, carrying information about their source and the geometry of the surrounding region. Unlike sound waves or water waves, these are distortions of the medium itself, not of something moving within it. Observing these ripples is akin to feeling the vibrations of a taut membrane from afar, a direct perception of spacetime's flexibility in action. Einstein's insight into spacetime revolutionized our understanding of gravity. No longer merely a force, gravity is a manifestation of the curvature of the fabric. Objects follow the straightest possible paths within this curved geometry, called geodesics. Planets orbit stars, moons orbit planets, and light bends around galaxies not because of an invisible pull, but because these paths are dictated by the shape of spacetime itself. The universe is therefore a network of geometrical rules, with curvature guiding motion and energy, seamlessly integrating matter, energy, and the geometry in which they reside. Even extreme objects reveal the fabric's flexibility. Black holes, regions where spacetime curves so intensely that not even light can escape, illustrate the limits of curvature. The fabric bends to an almost infinite degree, creating a singularity at the core. Yet, beyond the event horizon, spacetime remains continuous, responding to incoming matter and radiating gravitational waves during mergers. Neutron stars, though less extreme, also significantly warp the fabric, demonstrating that even comparatively small masses can imprint detectable curvature on spacetime, observable through precise measurement. Gravitational waves are traveling disturbances in this flexible medium. When black holes collide, spacetime stretches and compresses in alternating patterns, propagating outward like ripples on a pond. These ripples are tiny by the time they reach Earth, but they carry the imprint of the event with perfect fidelity. In essence, the fabric of spacetime itself records and communicates the universe's most energetic occurrences, allowing us to perceive collisions and explosions that emit no light. The flexibility of spacetime thus functions as a cosmic messenger, encoding events across time and space. Spacetime is also dynamic. Its geometry changes continuously as objects move and interact. Galaxies swirl, stars explode, and planets orbit, all while the underlying fabric bends, stretches, and adjusts. This dynamism is not restricted to localized events, it extends across the cosmos. The interconnectedness of curvature means that a massive collision in one region sends faint ripples through otherwise calm areas. Observing spacetime is therefore like listening to an orchestra where every motion, no matter how distant, contributes to the ongoing symphony. Even seemingly empty space is not truly void. It is filled with the potential to bend, stretch, and propagate waves. Dark matter, although invisible, contributes to the curvature of spacetime, shaping the formation of galaxies and clusters. The very large-scale structure of the universe, the cosmic web of filaments and voids, is determined by how spacetime flexes in response to mass. The flexibility of spacetime provides the stage for cosmic evolution, dictating how matter aggregates, how light propagates, and how time itself unfolds across billions of years. The flexibility of spacetime also integrates energy. Moving masses and radiation influence the curvature, and the curvature, in turn, influences motion. This reciprocity is central to general relativity. For example, a passing gravitational wave modifies distances, which can slightly alter the path of nearby objects. Even small changes ripple through the system, subtly affecting dynamics across scales. The universe is thus not a collection of isolated events, but a coherent continuum where geometry, energy, and matter interact constantly, the fabric itself mediating every interaction. Even time dilation is a manifestation of spacetime's flexibility. Clocks run slower in regions of stronger curvature, a direct effect of spacetime geometry on temporal intervals. Satellites in orbit must account for this when synchronizing GPS systems. Everyday technology, in fact, relies on the precise understanding of how spacetime bends and stretches. Flexibility is not just a cosmic curiosity, it has practical consequences, revealing that the universe's geometry is intricately connected to the very functioning of human devices and our measurement of reality. Spacetime's flexibility allows for the propagation of information in ways beyond light. Gravitational waves, for instance, move through matter with negligible attenuation. They carry unaltered messages about massive, distant events, reaching us across billions of light-years. The flexibility of the fabric is what permits these ripples to exist and propagate. It is a medium sensitive to energy and motion, yet resilient, transmitting information about the universe without distortion, enabling humanity to perceive phenomena otherwise entirely hidden. Even the most violent cosmic events illustrate spacetime's adaptability. Supernovae explosions, merging neutron stars, and black hole collisions all generate waves that propagate without tearing the fabric. Spacetime accommodates these disturbances, flexing and oscillating while remaining continuous. It is at once pliable and robust, capable of sustaining enormous energy flows and returning to a baseline curvature once the waves pass. This duality, strength and flexibility, defines the fabric and underpins the universe's capacity to host complexity over billions of years. The elasticity of spacetime explains gravitational lensing in vivid terms. Massive objects warp the paths of light rays, bending them along the contours of curvature. A single galaxy can act as a lens, magnifying distant objects behind it. The bending of light is thus a direct demonstration of spacetime's flexibility, making visible the otherwise hidden structure of the cosmos. Through these distortions, astronomers map dark matter, reconstruct cosmic history, and gain insight into the distribution of mass across billions of light-years. The fabric analogy also aids in imagining the early universe. Moments after the Big Bang, spacetime itself was dense, hot, and dynamic, vibrating under the influence of immense energy. As the universe expanded, the fabric stretched, cooling and forming the large-scale structures we observe today. Gravitational waves from those primordial epochs may still ripple through the cosmos, carrying information about conditions we cannot recreate. Spacetime's flexibility is therefore not just a present-day phenomenon but a window into the earliest stages of existence. Even on human scales, spacetime is flexible, though the effects are subtle. Earth's gravity bends spacetime around us, producing measurable time dilation between mountain peaks and valleys. High-precision experiments confirm that the fabric adjusts to every mass, every motion. Though imperceptible in daily life, this bending affects navigation, communications, and timing systems. The universal principle of flexibility thus operates seamlessly across scales, connecting the immense and the mundane in a single, coherent framework. The flexibility of spacetime provides a unified explanation for diverse cosmic phenomena. Orbital motion, light deflection, gravitational waves, and time dilation are all consequences of the same underlying geometry. There is no need to invoke separate forces for each effect. The bending and stretching of the fabric accounts for everything. This elegant simplicity is part of the power of general relativity, revealing that complexity in observation emerges naturally from a coherent, flexible, and interconnected cosmic medium. Even the emptiest regions of space have structure due to spacetime's flexibility. Quantum fluctuations, dark matter distributions, and gravitational interactions all imprint subtle curvature variations, shaping the motion of galaxies over billions of years. Spacetime is therefore a living map of the universe, encoding its history, dynamics, and potential futures. The fabric responds to all influences, large and small, creating a continuum in which every event, from the collision of black holes to the orbit of a satellite, is a manifestation of geometry in motion. The bending and stretching of spacetime also fosters wonder and humility. It reminds us that reality is far more intricate than sensory experience suggests, and that the universe is a responsive, interconnected continuum. Every mass contributes, every motion matters, and the fabric itself participates in cosmic storytelling. Understanding spacetime as a flexible fabric helps demystify gravity, light propagation, and cosmic dynamics while simultaneously inviting awe at the complexity, coherence, and elegance of the universe. Explain how massive accelerating objects, like black holes colliding, create these ripples. Imagine two black holes locked in an intricate cosmic dance, spiraling ever closer under their mutual gravitational pull. As they orbit, their immense masses warp spacetime more intensely, generating distortions that propagate outward. These distortions are gravitational waves, traveling at the speed of light, carrying information about the masses, speeds, and trajectories of the colliding objects. The waves themselves are subtle, yet they encode the violent energy released in the process. The acceleration of these massive objects is crucial. In general relativity, only changing mass distributions or accelerating masses produce gravitational waves. A stationary mass, no matter how enormous, creates curvature but not ripples. It is the dynamic motion, the spiraling, twisting, and colliding that shakes the fabric of spacetime. As the black holes accelerate toward each other, the curvature of spacetime oscillates, sending vibrations across the universe. Each orbital revolution contributes to a steadily increasing waveform, growing stronger as the objects draw closer. During the final moments of a collision, the effect is dramatic. The black holes accelerate to a significant fraction of the speed of light. The warping of spacetime intensifies, producing waves with increasing amplitude and frequency, a characteristic chirp detected by observatories like LIGO. The chirp reflects both the masses of the black holes and the rapid acceleration preceding the merger. These ripples are not mere metaphor, they are literal expansions and contractions of distances along perpendicular axes, a measurable stretching and squeezing of spacetime itself. The energy involved in these events is staggering. In a few seconds, the merger can release more energy in gravitational waves than the combined electromagnetic output of all stars in the observable universe. Yet, by the time these waves reach Earth, the distortions are minuscule, smaller than a proton over kilometers. This incredible attenuation highlights the subtlety of gravitational waves. Even the most cataclysmic cosmic events send ripples that require extraordinary sensitivity to detect, underscoring the elegance and resilience of spacetime's fabric. Gravitational waves carry detailed information about their sources. The amplitude encodes the total mass, the frequency reveals the orbital speed, and the waveform shape provides insight into the spins and orientations of the black holes. By analyzing these ripples, scientists can reconstruct events that occurred billions of light-years away. It is a direct reading of cosmic geometry, a translation of spacetime motion into comprehensible data. Each wave functions as both a messenger and a record, conveying the dynamics of accelerating massive bodies across the cosmos. Acceleration is essential because gravitational waves are quadrupole in nature. A simple back-and-forth motion does not produce them. Instead, asymmetric, time-varying distributions of mass are required. Black holes orbiting each other naturally produce such asymmetry, creating a quadrupolar distortion that propagates outward. The fabric of spacetime is stretched along one axis while compressed along another, alternating rhythmically as the bodies orbit. This quadrupole pattern is a fundamental feature of gravitational radiation, distinguishing it from other forms of energy emission. As the black holes draw nearer, the orbital period decreases, and the wave's frequency increases. This phenomenon, called a frequency sweep or chirp, is the signature detected on Earth. It is analogous to the rising pitch of a siren as an ambulance speeds by, except the medium is spacetime itself. The waveform grows in both amplitude and frequency until the merger occurs, after which the newly formed black hole settles into a stable state, radiating a final ringdown signal. Each phase encodes a different aspect of the accelerating body's dynamics. The process is inherently nonlinear. The greater the mass and the closer the approach, the stronger the distortions. The interaction of the black holes with spacetime becomes a feedback loop. Acceleration generates waves, waves carry energy away, and the loss of energy accelerates the merger. This self-reinforcing cycle culminates in the most violent moments of cosmic motion, when the waves carry away a significant fraction of the system's mass energy, leaving the resulting black hole lighter than the sum of its progenitors. Gravitational waves also propagate outward with polarization patterns determined by the acceleration vectors of the bodies. These patterns stretch and compress space along perpendicular axes, alternating in orientation as the waves pass. Observatories detect these tiny shifts in arm lengths, confirming the quadrupolar nature predicted by Einstein. The precise measurement of these polarizations allows scientists to infer the orientation of the orbit, the inclination relative to Earth, and even subtle details about spin interactions between the colliding black holes. Even neutron-star collisions follow similar principles, though they often involve matter as well as spacetime distortions. The accelerating, asymmetric mass distributions of dense neutron stars produce gravitational waves, while tidal forces and internal dynamics influence the waveform. These events can be accompanied by electromagnetic signals, allowing multi-messenger astronomy, but the gravitational waves themselves remain direct signatures of acceleration-induced spacetime ripples. They reveal the structure, mass, and motion of these dense objects in exquisite detail. The farther the waves travel, the weaker their amplitude becomes, yet the information they carry remains intact. Unlike light, gravitational waves interact extremely weakly with matter, passing through galaxies, stars, and interstellar gas unimpeded. The acceleration at the source imprints geometry onto the waves, and this imprint travels unaltered. In this sense, spacetime acts as a near-perfect messenger, faithfully transmitting information about the dynamics of massive accelerating bodies across billions of light-years. The bending and stretching caused by acceleration is not uniform in all directions. Depending on the orientation of the orbital plane and the mass ratio of the objects, certain directions experience stronger distortions. This directional dependence allows networks of detectors to triangulate the source location, providing not only the physical parameters but also the spatial coordinates of the accelerating system. The interplay of acceleration, geometry, and orientation produces a rich variety of gravitational waveforms, each telling a unique story about the cosmic choreography that produced it. Accelerating masses also generate higher harmonics in the waveform, reflecting subtle features of the motion. Precession of spins, eccentric orbits, and asymmetries in mass distribution contribute to these harmonics. By analyzing them, scientists can deduce detailed properties of the system, including the degree of orbital eccentricity, the relative spin alignment, and even potential deviations from general relativity. Each tiny modulation in the waveform is a fingerprint of acceleration, revealing how the body's motion imprints itself on the very fabric of spacetime. Theoretical models using numerical relativity simulate these processes. By solving Einstein's equations for massive accelerating systems, scientists predict the exact form of gravitational waves for a given collision scenario. Observed signals are then compared to these templates, confirming both the source properties and the validity of the theory. This synergy between observation, acceleration, and mathematical modeling demonstrates that spacetime ripples are not abstract concepts, they are precise consequences of mass in motion, measurable and interpretable by human ingenuity. Acceleration also explains the timing of the wave. As the orbit shrinks, the acceleration increases, causing the frequency to rise. This culminates in a rapid crescendo at merger. Observing this timing allows scientists to reconstruct the in-spiral process, understanding how the black holes lost orbital energy and angular momentum through gravitational radiation. The waves are therefore not static, they carry a dynamic story of acceleration and interaction, tracing the journey from initial orbit to final union. The strength of the waves depends strongly on mass. More massive black holes produce stronger distortions, while less massive systems create weaker signals. This relationship is not linear, however. Doubling the mass produces more than double the amplitude because gravitational wave generation scales with the system's quadrupole moment. The acceleration, mass distribution, and orbital configuration together determine the shape and intensity of the ripples that propagate outward into the cosmos. Even the ring-down phase after the merger reflects acceleration dynamics. The newly formed black hole, initially distorted and vibrating, emits gravitational waves as it settles into equilibrium. This ringing is a direct response to the violent acceleration at the moment of merger, a fading echo of spacetime readjusting to the new mass configuration. The frequency and damping time of these waves reveal the mass and spin of the remnant black hole, demonstrating that acceleration leaves a lasting imprint on the fabric of spacetime. Acceleration produces waves across multiple scales. Close to the black holes, spacetime is violently distorted, while farther away, the waves propagate as gentle oscillations. The amplitude diminishes with distance, but the signature remains detectable. This propagation illustrates the universality of spacetime's response. The same laws govern both the immediate extreme curvature near the source and the subtle ripples reaching Earth. The acceleration at the source imprints a message that travels across billions of light-years, unaltered by intervening matter. Even minor asymmetries in acceleration can produce observable effects. Unequal mass ratios, misaligned spins, or orbital precession generate unique waveform features. These details allow scientists to distinguish between different types of mergers and study how variations in acceleration influence the resulting gravitational waves. Every nuance of motion, every slight deviation from symmetry, contributes to the richness of the signal, offering an unprecedented window into the complexity of massive, accelerating cosmic objects. The production of gravitational waves demonstrates energy transfer from matter to spacetime itself. Accelerating masses lose orbital energy through radiation, which escapes as ripples. This loss causes the orbit to decay and the bodies to spiral closer, creating a feedback loop. Acceleration produces waves, which extract energy, further accelerating the merger. The process is self-reinforcing, culminating in the dramatic final collision. It exemplifies the intimate connection between acceleration, energy, and the geometry of spacetime. Acceleration also influences the polarization of the waves. Gravitational waves have two fundamental polarizations, plus and cross, which manifest as stretching and squeezing along perpendicular directions. The exact pattern depends on the acceleration vectors of the colliding bodies. Measuring the polarization provides insight into the orientation of the system relative to Earth, adding another layer of understanding to the ripples generated by massive accelerating objects. Even in hypothetical scenarios, acceleration governs wave production. Triple systems, eccentric binaries, and hyperbolic flybys all produce gravitational waves according to the changing motion of mass. The fundamental principle remains: any non-uniform acceleration of mass generates ripples in spacetime. The universe is therefore alive with signals, though only the strongest events are currently detectable. Acceleration is the engine, spacetime the medium, and the resulting waves the message transmitted across the cosmos. Finally, the detection of waves from accelerating black holes confirms both the predictions of general relativity and the reality of spacetime as a flexible, responsive fabric. Each observation is a testament to how dynamic motion at immense scales imprints itself on the universe. The collision, spiraling, and merging of black holes demonstrate that acceleration is not merely a kinematic detail, it is the fundamental driver of ripples in spacetime, the mechanism by which the universe communicates its most violent and energetic events across incomprehensible distances. Use an analogy: it's like dropping a bowling ball onto a trampoline. The surface dips, and ripples expand outwards. Picture the trampoline as the fabric of spacetime. When the ball lands, the sheet sags beneath its weight, curving around it. Smaller objects placed nearby will roll toward the dip, not because they are pulled by some invisible force, but because the surface itself has deformed. Similarly, massive objects like stars and black holes bend spacetime around them. The trampoline illustrates how gravity emerges naturally from curvature rather than from a mysterious force acting at a distance. As the bowling ball moves, oscillations form across the trampoline. Each bounce sends waves radiating outward. In the cosmos, accelerating massive objects, particularly those in binary orbits, produce similar ripples in spacetime. These gravitational waves expand outward at the speed of light, carrying information about the motion and mass of their sources. The trampoline analogy helps visualize how dynamic motion, not just presence, generates disturbances that propagate through a flexible medium, subtly influencing everything along their path. Consider the size of the ripple relative to the ball. On a trampoline, a bowling ball creates noticeable undulations, while a marble barely dents the fabric. In space, the mass of a black hole or neutron star determines the strength of the gravitational waves. Larger masses produce larger amplitude ripples. This analogy emphasizes the relationship between mass and effect. The greater the mass and acceleration, the more pronounced the ripples in spacetime, just as a heavier bowling ball causes deeper and more extensive oscillations across the trampoline. The analogy also illustrates distance attenuation. On a trampoline, the ripples are strongest near the point of impact and weaken as they move outward. Gravitational waves behave similarly, the closer to the source. The more intense the spacetime distortions, the farther away, the subtler they become. By the time waves reach Earth from distant mergers, the effect is tiny fractions of a proton's width, yet detectable with sensitive instruments. This scaling underscores how energy disperses through a medium, whether trampoline or cosmic fabric. Acceleration is key to ripple formation. A ball sitting still on the trampoline creates a dip but no expanding waves. Only when it moves or oscillates do ripples form. Likewise, stationary masses bend spacetime, creating static curvature, but only accelerating masses generate traveling gravitational waves. Binary systems of black holes, neutron stars, or even asymmetric supernovae accelerate as they orbit, collide, or explode, producing propagating distortions that travel across the universe. Motion is essential to the production of these spacetime ripples. The trampoline analogy helps visualize wave propagation. The surface is temporarily distorted, and the deformation travels outward in rings. Gravitational waves similarly stretch and compress spacetime as they move, altering distances perpendicular to their direction of travel. LIGO detects these minute oscillations by measuring changes in length along two perpendicular arms. The expanding ripples from the cosmic bowling ball demonstrate that the medium itself carries information, communicating the motion of massive objects across vast distances. Multiple balls create complex interactions. Drop two bowling balls near each other on a trampoline, and their ripples interact, merging, amplifying, or cancelling in places. In the universe, multiple accelerating objects create overlapping gravitational waves, producing interference patterns. Observatories analyze these superimposed signals to disentangle sources and understand the dynamics of multiple colliding systems. The trampoline analogy illustrates that waves are not isolated, they combine, interact, and produce intricate patterns that convey detailed information. Consider the speed of ripple propagation. On a trampoline, waves travel at a rate determined by the sheet's tension and mass. In spacetime, gravitational waves move at the speed of light. The speed sets a fundamental limit on how quickly information about massive accelerating objects reaches distant observers. The analogy underscores that while the wave's effects are subtle far away, the information they carry is faithfully transmitted across vast cosmic distances. Just as a ripple carries the motion of the ball across the trampoline surface. Ripples diminish with distance but retain structure. On a trampoline, even as waves weaken, the pattern reflects the original impact. Gravitational waves similarly preserve details of their sources, including mass, spin, and orbit. Observing these subtle distortions allows scientists to reconstruct events billions of light-years away. The analogy emphasizes that the medium encodes and transmits information, whether the trampoline holds the memory of the ball's motion or spacetime encodes the story of a black hole merger. The analogy also shows quadrupole behavior. When a heavy ball distorts a trampoline unevenly, the surface stretches along one axis while compressing along the perpendicular axis. Gravitational waves have this quadrupolar nature. As they pass, spacetime alternately stretches and squeezes in perpendicular directions. Instruments like LIGO measure this stretching and squeezing to detect the wave. The trampoline example helps translate an abstract geometric concept into something intuitive and visualizable. Oscillations grow stronger with acceleration. On the trampoline, a ball dropped from a greater height produces higher amplitude ripples. Similarly, the faster and more violently massive bodies accelerate, the more energetic the gravitational waves. Binary black holes, nearing collision, accelerate dramatically, generating the highest amplitude waves at the moment of merger. The analogy clarifies why acceleration, rather than mere mass, governs the intensity of the ripples in spacetime. Multiple frequencies emerge in complex motion. A bouncing bowling ball produces primary waves along with smaller, faster oscillations. In astrophysical systems, eccentric orbits or asymmetric collisions produce higher harmonics in gravitational waves. Each oscillatory mode encodes unique information about the source, revealing details of mass distribution, spin, and orbital eccentricity. The trampoline analogy helps conceptualize how complex motions produce rich, multi-frequency wave patterns across a flexible medium. Wave interference patterns arise naturally. Two ripples meeting on a trampoline amplify in some regions and cancel in others. In the universe, overlapping gravitational waves from different events create constructive and destructive interference. Observatories must carefully isolate signals to decode the information about each source. This behavior underscores that the fabric is not just reactive but interactive, with waves combining to produce new patterns that still carry the imprint of the originating acceleration. The trampoline analogy also illustrates memory effects. After the ball stops moving, small oscillations may linger, slightly adjusting the sheet's shape. Gravitational waves can leave a permanent imprint in spacetime, a phenomenon called gravitational wave memory. Though subtle, this effect suggests that the universe records the passage of massive accelerating events, leaving a lasting geometric mark analogous to a lingering dent in the trampoline's surface. Energy transfer is evident. The moving ball transfers kinetic energy to the sheet, creating ripples. Likewise, accelerating masses lose orbital energy through gravitational wave emission, which propagates through spacetime. This loss causes inspiraling orbits to shrink, driving mergers. The analogy helps visualize the intimate connection between motion and energy dissipation, showing that spacetime is not passive, it absorbs and conveys energy from accelerating bodies. The analogy extends to scale. On a trampoline, ripples span the surface, limited by its size. In spacetime, Ripples can traverse billions of light-years, unimpeded. While the trampoline is finite, the universe is vast, illustrating that gravitational waves can communicate information across cosmic distances, retaining the signature of their originating acceleration even over enormous scales. The scale difference highlights the subtlety and persistence of spacetime distortions. Non-spherical impacts create asymmetric ripples. A tilted or unevenly dropped ball produces complex oscillations. Similarly, colliding black holes or neutron stars rarely have perfectly symmetrical orbits. Asymmetries in mass or spin generate distinctive waveform features, encoding detailed information about the system. The trampoline analogy helps visualize how initial conditions of the impact shape the evolving pattern of waves, emphasizing the richness of the signals created by accelerating massive bodies. Amplitude modulation occurs naturally. On a trampoline, the size of ripples changes depending on bounce height and frequency. Gravitational waves exhibit similar modulation. As black holes spiral inward, the amplitude increases, reaching a peak at merger. This crescendo is directly related to acceleration, analogous to dropping the ball from increasing heights. Observatories detect these amplitude changes, allowing reconstruction of orbital dynamics and energy dissipation. The trampoline analogy also conveys directionality. Waves expand outward in concentric circles from the point of impact. In spacetime, gravitational waves propagate in all directions from the accelerating mass, though detectors measure them along specific axes. Directionality helps scientists determine the location of the source, much like tracing the origin of ripples on a sheet. The analogy emphasizes that acceleration creates an outward spreading signal, not a localized, static deformation. Velocity of propagation matters. Ripples on a trampoline travel slower than the speed of the ball, determined by the fabric's tension. In spacetime, the speed is fixed at the speed of light, making gravitational waves fast messengers across the cosmos. This analogy underscores that while the medium may be flexible, there is a finite propagation speed, carrying the information of the acceleration faithfully from source to observer. Phase relationships are visible. Ripples from multiple balls on a trampoline can be in or out of sync. In gravitational waves, the phase encodes timing information about the accelerating bodies. Waveform analysis allows reconstruction of orbital phases, spin orientations, and merger timing. The trampoline analogy illustrates how relative motion affects the ripple's alignment, translating complex mathematical details into visual intuition. The analogy extends to resonance. Continuous or repeated acceleration produces sustained oscillations on the trampoline. Similarly, spiraling binaries emit waves over many orbits, producing a sustained gravitational waveform detectable over time. The continuous emission carries cumulative information about mass, spin, and orbital characteristics. The trampoline helps conceptualize how ongoing acceleration generates a persistent signal rather than a single, isolated disturbance. Energy distribution is uneven. On the trampoline, ripples near the ball are larger, while those farther away are smaller. In spacetime, gravitational wave amplitude decreases with distance, yet the pattern remains intact. Observatories detect these subtle signals, revealing the energy released in the accelerating system. The analogy demonstrates how acceleration governs not only the generation but also the propagation of energy through a flexible medium. The analogy also explains observatory sensitivity. Just as tiny ripples on a trampoline might require careful observation, detecting spacetime distortions requires exquisitely precise instruments. LIGO measures changes smaller than a proton, analogous to detecting the smallest oscillations on a large sheet. The analogy emphasizes that while the effect of acceleration is universal, perceiving it demands extraordinary care and precision. Interaction of multiple accelerations can create complex patterns. If several balls are dropped in sequence or simultaneously, ripples interfere, producing constructive and destructive patterns. Similarly, in dense stellar environments, multiple accelerating bodies create overlapping gravitational waves. Observatories untangle these signals to understand individual events. The trampoline analogy captures how superposition shapes the observed waveforms, turning complex acceleration into decipherable patterns. Finally, the trampoline analogy encapsulates the essence of spacetime's responsiveness. Mass and acceleration bend, stretch, and ripple the medium, transmitting energy and information outward. Just as we can infer the motion of the ball by observing ripples on the sheet, we can infer the properties of colliding black holes and neutron stars by analyzing gravitational waves. The analogy bridges the gap between intuition and cosmic phenomena, making the otherwise abstract concept of ripples in spacetime accessible and tangible. Introduce the incredible precision of observatories like LIGO and Virgo. Imagine trying to measure a change in distance smaller than the width of a proton across a span of 4 kilometers. This is exactly what LIGO, the Laser Interferometer Gravitational Wave Observatory, accomplishes. Using laser beams split along perpendicular arms and reflected by mirrors, it detects minute differences in length caused by passing gravitational waves. The precision is so extraordinary that it transforms an almost imperceptible cosmic ripple into measurable data, confirming the presence of waves predicted by Einstein a century earlier. The design of LIGO is a marvel of engineering. 2 perpendicular vacuum arms stretch 4 kilometers, each containing mirrors suspended by intricate isolation systems to prevent even the slightest vibration from interfering. Laser beams traverse these arms, reflecting back and forth to detect minuscule differences in travel time. When a gravitational wave passes, it stretches one arm while compressing the other, altering the interference pattern of the laser light. This change is measured with sensitivity far beyond ordinary human experience, revealing ripples in the fabric of spacetime. Virgo, located in Italy, complements LIGO by providing additional measurement points. By comparing signals from multiple observatories, scientists can triangulate the location of gravitational wave sources across the sky. The collaboration of detectors improves confidence, eliminates false positives, and enhances the precision of inferred properties such as distance, mass, and spin of colliding objects. Together, LIGO and Virgo form a network capable of perceiving distortions in spacetime that are billions of times smaller than the width of an atom. The technology relies on isolating the detectors from virtually all environmental noise. Vibrations from traffic, seismic activity, or even distant storms can mask signals if not carefully mitigated. Advanced suspension systems, vacuum tubes, and active feedback mechanisms reduce these interferences to negligible levels. It is remarkable that the instruments can distinguish between gravitational waves traveling across the cosmos and tiny disturbances originating in the immediate surroundings, demonstrating the extraordinary precision and sensitivity of modern gravitational wave observatories. Laser interferometry is the key to this sensitivity. A laser beam is split into 2 perpendicular paths, travels down each arm, and reflects off mirrors to recombine at a detector. Any difference in length caused by a gravitational wave alters the phase of the returning light, creating an interference pattern that can be measured. The changes detected are astonishingly small, less than 1 part in 10 squared to the power of 1, highlighting both the subtlety of gravitational waves and the technological sophistication required to observe them. The precision of LIGO and Virgo also allows scientists to extract detailed information about the sources. By analyzing the waveform, they determine the masses, spins, orbital orientations, and distances of colliding black holes or neutron stars. The interferometers do not merely detect the waves, they encode the cosmic story. Each ripple carries a signature of the source's dynamics, and the precision of the instruments ensures that even the most subtle details are recorded and interpreted accurately. The challenge of calibration cannot be overstated. Mirrors, lasers, and detectors must be aligned to extraordinary tolerances. Even thermal fluctuations can affect the measurements, so temperature control and stabilization are essential. Laser light must remain coherent over the entire 4-kilometer path, requiring meticulous maintenance and feedback systems. The sheer exactness of these instruments is a testament to human ingenuity, allowing observation of phenomena that, without such precision, would remain forever beyond our sensory reach. Seismic isolation is a critical component. Ground vibrations, though imperceptible to humans, are enormous compared to the displacements caused by gravitational waves. Multi-stage pendulums and active damping systems reduce these effects, preventing contamination of the signal. The precision achieved is such that LIGO can detect movements smaller than 1/1000th of a proton's diameter, an astonishing accomplishment that underlines the careful engineering and deep understanding of physical principles required to observe gravitational waves. The sensitivity of these detectors has steadily improved over time. Initial LIGO had remarkable capabilities, but advanced LIGO upgrades increased sensitivity by a factor of 10, expanding the volume of space observable for gravitational wave events by 1,000-fold. This enhancement allows detection of more distant mergers and weaker signals, revealing events previously hidden. The precision is not static, it evolves, reflecting the ingenuity and dedication of scientists and engineers continually refining the observatories to push the boundaries of human observation. Noise reduction extends to quantum limits. Even the uncertainty principle imposes limits on measurement. To mitigate this, techniques like squeezed light are employed, reducing quantum noise in the interferometer. This allows detection of signals even closer to the fundamental limits set by physics itself. The precision achieved is therefore not merely engineering but a dance with the laws of quantum mechanics, harnessing subtle effects to peer deeper into the universe than ever before. The detectors also function in a network, providing redundancy and verification. LIGO operates 2 sites in the United States, while Virgo provides a European anchor. Simultaneous detections at multiple sites confirm the astrophysical origin of signals, ruling out local disturbances. Timing differences between detections help pinpoint the sky location of sources. The coordination among these high-precision instruments transforms individual measurements into a global system capable of mapping space-time ripples across vast distances. The mirrors themselves are engineering marvels. Made of ultra-pure glass and polished to atomic smoothness, they are suspended by multiple stages of pendulums to isolate them from vibrations. Any imperfection could introduce noise or distort measurements. Their stability and reflectivity are essential to achieving the sensitivity needed to detect minuscule space-time ripples. This meticulous attention to detail is a critical reason why gravitational wave astronomy became possible, transforming theory into measurable reality. Even the vacuum systems are extraordinary. The 4-kilometer arms are maintained at near-perfect vacuum, eliminating the effects of air molecules on laser propagation. Any residual air could scatter or refract the laser, masking the subtle signal. Maintaining this vacuum over such distances and for extended durations is itself a technical feat, allowing the laser to traverse the interferometer arms unimpeded, sensitive enough to detect the tiniest spacetime distortions produced by distant cosmic collisions. The observatory's precision allows for verification of Einstein's predictions with remarkable accuracy. Waveforms detected match theoretical models based on general relativity, confirming the nature of spacetime as a flexible, dynamic fabric. The detection of multiple events provides statistical validation, ensuring that observations are not anomalies. LIGO and Virgo's incredible sensitivity transforms abstract mathematical theory into tangible measurement, bridging centuries of thought with modern technological achievement. Environmental monitoring complements precision measurement. Thousands of sensors record seismic activity, electromagnetic interference, and acoustic vibrations. These data streams help identify and subtract noise sources, ensuring that detected signals are genuine. This layered approach demonstrates that precision is not solely about the instrument but also about understanding and compensating for the environment, creating a system capable of isolating the faintest whispers of space-time ripples from the overwhelming noise of daily life. Timing is essential. Gravitational waves travel at light speed, and the small differences in arrival times between observatories allow triangulation of sources. Precision clocks and synchronization systems maintain accuracy down to microseconds. These measurements not only detect the waves but also map the location of astrophysical events billions of light-years away. The interplay of timing and sensitivity illustrates the sophistication of modern observatories, transforming infinitesimal distortions into cosmic cartography. Data analysis depends on precision too. Raw measurements must be filtered, cross-correlated, and compared with theoretical templates. Even the slightest calibration error could misinterpret the waveform. LIGO and Virgo's precision ensures that data is reliable, and computational techniques allow scientists to extract parameters of the source with confidence. The combination of hardware accuracy and software rigor enables gravitational wave astronomy to deliver both discovery and insight. The precision extends to strain sensitivity. LIGO can detect a strain, a fractional change in length, on the order of 1 part in 10 squared to the power of 1. This sensitivity is equivalent to measuring a change smaller than a proton over 4 kilometers, a feat that borders on the inconceivable. It is a measure of human achievement, allowing instruments to respond to ripples caused by events billions of light-years away. This capability defines a new era in observational astronomy, where subtle distortions of spacetime become readable signals. The interferometers also detect polarization, revealing information about the orientation and geometry of wave sources. Precision in measuring how space stretches and compresses along perpendicular axes allows scientists to infer whether black holes were spinning, the angle of their orbital plane, and even aspects of their pre-merger motion. Observatories' sensitivity makes it possible to extract these subtle geometric details from an otherwise nearly imperceptible effect, demonstrating the power of combining high-precision measurement with sophisticated theoretical modeling. Thermal noise is another obstacle overcome by precision engineering. Mirrors and suspensions are designed to minimize thermal vibrations, which could obscure the signal. Even tiny temperature variations are controlled, with materials selected for stability and low absorption. These measures ensure that the interferometers remain sensitive to spacetime distortions at the limits of detectability, emphasizing that achieving such precision requires attention to every possible factor, from atomic scale vibrations to cosmic scale signals. Laser stability is critical. The interferometer relies on an extremely coherent, stable laser source. Any fluctuation in frequency or intensity could mimic or mask a gravitational wave signal. Advanced control. Systems monitor and correct for even the tiniest variations, ensuring that the detected interference patterns reflect spacetime ripples and not instrumental artifacts. This demonstrates that precision in gravitational wave detection is an orchestration of multiple high-fidelity systems, each contributing to the overall sensitivity. Even minute mechanical vibrations are countered with active feedback. Mirrors are suspended in multi-stage pendulums, and sensors detect motion at picometer scales. Actuators adjust the mirrors in real time, keeping the system stable against vibrations that would otherwise overwhelm the signal. This feedback is essential for maintaining the extraordinary precision necessary to measure the tiniest distortions caused by gravitational waves, exemplifying the intricate engineering behind observing cosmic phenomena. Gravitational wave observatories are also capable of distinguishing between different astrophysical sources. By precisely measuring waveform amplitude, frequency, and phase, they differentiate between black hole mergers, neutron star collisions, and other exotic events. The precision ensures that even subtle differences in acceleration or mass distribution are captured, allowing scientists to identify the nature of the accelerating massive objects producing the ripples in spacetime. The global network of observatories further enhances precision. LIGO and Virgo work in coordination, cross-verifying signals, reducing uncertainty, and refining source localization. Differences in arrival times, waveform shapes, and amplitudes across sites improve the accuracy of inferred properties. This international collaboration amplifies the precision achievable at a single site, illustrating how combining sensitive instruments enhances observational power and confidence in results. Finally, the incredible precision of LIGO and Virgo transforms human understanding. They convert infinitesimal distortions into profound insights about the universe, confirming theories, revealing unseen cosmic events, and opening new windows into spacetime. These observatories demonstrate that with meticulous engineering, careful calibration, and international collaboration, humanity can perceive the almost imperceptible fabric of reality bending and rippling across billions of light-years, bridging imagination, theory, and observation in unprecedented ways.